And welcome back. Let's see how we can make weird features like this. This is a 90-degree OD thread with 2.5mm pitch and a blunt start. And the idea here is to have a router motor. In this case it's a Crest router motor with ER16 collets mounted to the tool post of the lathe and have it either square to the spindle or in line with the spindle. And this allows me to do, for example, thread milling on a manual lathe, which is normally done on a CNC mill or on a CNC lathe. Less so known on manual machines, but it was done. For some manual production lathes, there were thread milling attachments. I'm not the first one to do this. I'm not the last one to do it. I didn't invent this, but that's my take on it now. So let's look at this mounting block here first, how I made this, and then set it up here in the lathe and do some thread milling. Okay, I started by laying out some lines on some 50mm mild steel and bandsawed the shape out, face milled it to size, use a rotor broach to remove most of the material from both sides because the cutting depth was not enough, and then I used a wall deburring head to cut it to final size. Then a little bit more band sawing to get it to final shape, some drilling, sawing, tapping, and that's the end result. There is really not much to this part. Haven't done much deburring on camera lately, so why not do this one? We'll start with a die grinder and always go climb cut. Never go conventional cut against the rotation because you will dig in. When you go climb cut this direction, it will always ride on the material and not cut into it. That way you get a very clean and easy controllable chamfer. Okay, I deburred everything that I can reach easily with the die grinder, and it's already handling way nicer. This keyway slot here needs some more work. This is needle file work, and we will just hit it like this with a file. Go 45 into the corner, so we get a nice mitered chamfer in the corner. Same for the edge that touches it. Always also 45 compound angle. And create a nice mitered chamfer in there. Hey, you're dragging the file on the backstroke. Yeah, I'm filing and I'm releasing pressure and I drag it back. Same here, filing all the way up into the corner or compound angle, falling over the corner here. Same here, falling over and mitered chamfer all the way into the corner. This doesn't have to be a science project. This is just a very, very utilitarian tool. But I still want to do a decent job. Take everything that we did with the die file, with the die grinder, and put a secondary chamfer on there. So it's almost a radius. This goes very quick. This takes only a few minutes. And with what we're about to do, doesn't need to be super tidy. The magic will come later. There are 2 apprentice marks in here, and somebody slipped with the die grinder minorly here, but we'll go with that. We will leave it like that. Some 200 grit sanding sponge. Usually I have way coarser ones because they cut faster, but I'm out of them, so I have to use the 220 stuff. And then we just hit every edge corner and also the surfaces with the stuff. And this unifies everything. This just makes it look crazy nice, and this doesn't take long. We don't have anything off here. I'm not running very rough lid off. Nice. And then. Ready to go. We will put some screws in the threads so we don't sandblasting and threads don't go together all too well. So we protect these with some scrap screws. Okay, that's the touch everything with both hands, cut yourself test. If you still cut yourself or hurt yourself, you didn't deburr it properly. That's like the guy standing next to the cannon that he cast on its first test fire. And if it blows up, well, didn't cast it good enough. Cannon blowing up is of course worse than cutting yourself on a badly deburred part, but still, same idea. Not crazy. Did the sandblasting on these parts, and they don't look too shabby. A little bit grummy from my finger, from oily fingers, but that's not an issue. We take those screws out. And I changed my mind again, and I'm going not to leave it blank metal. I'm going to black oxide it, cold blue. This part is small enough, and the steel is mild steel, so or low carbon steel, so the black oxide will work just fine on it. And the blasted finish will make it work very nicely. Let's put on some gloves, because we're working with some with a number of chemicals here. First one is an activator. This is an acidic activator that attacks the surface of the material and makes it more susceptible to the reaction of the actual cold blue. Okay, first we wash the part down with some acetone. Then there is a thing about the chemicals. I don't take a brush or something and dunk it into the chemicals I'm going to use, especially in the cold blue, because you will cross-contaminate back from the part into the container and just ruin it, especially with the cold blue. When you get any oil or something like that back into the cold blue, yeah, it doesn't work that well anymore. So I use a cotton swab, clean cotton, and I just put some of the activator solution on there, and I wipe down all surfaces of the part that are relevant. Eye protection, of course, it's an acid, and the cotton swab technique works exceptionally well. I had best results. I tried different other ways to do this, and everything else just ended up being a blatant mess. And this has proven for me to work the best for these small parts that I usually do. So we hit all surfaces nice and even. And the part needs now to rest a little bit, about, I think they say something like 5 minutes. So the acid can do its magic on the metal. Now, a few minutes later, we take our part and some distilled water, and we wash the activator solution off. My experience, it just needs to be kind of cleanish. You don't need to dry them. The cold blue works in conjunction with the water just the same. It just gets a little bit diluted. That's not an issue. fresh cotton swab for the cold blue. Oh, let's take a little bit more of a cotton swab here. Cold blue, selenium dioxide based cold blue. There is no special brand that I recommend. Just get something. Get it on the cotton swab, and here we go. Whoop. And there is the reaction. And then we just wipe down the whole surface of the part in a timely manner. And that looks already pretty darn good. If you put the part on a hot plate and heat it up a little bit, maybe 50 degrees C or something like that, the reaction gets even faster. Sometimes, depending on the alloy of the steel, you also get bluing, a real blue and not a black or dark brown. You take your denatured water again and you rinse the parts off. And then you immediately need to oil them. I like to use a spray lubricant because they are usually very, very thin and go in every corner. That's what we're going to do now. Take a fresh piece of paper. I will rinse the parts off camera. And you have to be a little bit quick after rinsing because the black oxide is basically rust. And rust in combination with water means more rust. So you don't want to leave the part sitting around like that forever. Otherwise, you might be in for a surprise. Okay, here's the spray lubricant. I use some oil. And I spray the part down. Extra care taken on threads and bores. So you don't get a rusty surprise in there. And now you have to leave the part sitting for some time. The freshly built black oxide, which is an oxide layer, is porous and it will soak up some of the oil during that time and create not exactly a rust protection, but the parts don't rust immediately. Usually these parts, after you rinse them and you spray them down with oil, they seem to go a little bit darker in color, more towards black or bluish black, which is nice. Okay, the oil has soaked in, I wiped it all down, and now it's time to put this to use. And when I bored this 43mm bore, which is a Euro standard for these router motors, and also hand drills, electric ones, have this 43mm shank. I made it basically 0-on-0 fit, so you cannot assemble this. You would have to pound a screwdriver in there and spread it apart, which is, you don't do that. I added a set screw in the center here, which allows me, if you back up the clamping screws a little bit, to spread this clamping element apart a little bit. Then it goes on very nicely. You can adjust it. Then you back off the screw. Then it's already basically held in place. You can almost not move this by hand, or in fact, you cannot. And then the only thing that's left is to tighten these screws like this. Just give it a little bit of torque. No need to crank down on it like crazy. These are only M4 screws. And that way, this clamping collar, if you make them right on size, you need basically almost no clamping force on the screws to make them hold properly. I screwed the key in here, and we take one of our Multifix holders. This happens to be tool number 15. Okay, so we put this in the Multifix holder. We press the holder up against the other holder. And we screw it down. And there is another design decision. This key, which is the clamping latch, does not touch the back of the Multifix holder. This face of this holder, this touches instead on this face, and this gives basically like a dual phase contact, like an HSK taper. You have contact here and you're clamping here on the thickness. So you add stiffness against bending load down and upwards. A router motor I'm using is a Cress FME-P. P stands for precision. No joke, it's really precision variants of this router motor. And the cool thing about it, it uses, compared to normal routers which use some stupid proprietary collets, this one uses ER16 collets, which is a big bonus in my book, because ER collets are readily available in all diameters, which are router collets usually not. So yeah, that's the package. This router motor goes from 5,000 to 25, so we have quite a speed range to play with. Gets super loud above 20,000 RPM because it's a brushed motor, brushed universal motor. But there it is. There is the live tool. I got the router with a Multifix holder mounted on the lathe, and I'm using a dial test indicator in the spindle of the lathe to center the spindle of the router in relationship to the lathe spindle, especially on height. On diameter it's not as critical because we can later touch off. And yes, I'm indicating with a rotating indicator, and we will have some indicator sag. But with this relatively short overhang, it shouldn't be that big of an issue. We don't have a no-go arm hanging out that far and indicating that way. In this case, it's probably like 20 or 30 micron of sag. And while we're here, we can also look at the runout of the router, and that's well within 10 micron, which is for a router motor not too bad. Let's get rid of the indicator. What can we do with this? We could chuck an end mill in here and drill and mill features on the end of a part. Cross slots, bolt hole pattern. If we put a dividing disc on the back end of the spindle of the lathe, we could drill, for example, bolt hole patterns or stuff like that. But I didn't do that. I didn't build this for this purpose. I'm not too interested in that. My main idea was thread milling. I want to do thread milling on the lathe. Every CNC guy, everybody who runs a CNC mill or a CNC lathe with a C-axis, C and Y-axis preferably, knows about thread milling. But why not do it on a manual mill? And I'm not the first guy to do this. This is not my invention, but this is my approach to it. Let's say it that way. So thread milling, you have a rotating form cutter that has a thread profile, and you have a spinning workpiece, and you have an overlaying cross feed, lengthwise feed, just as you would single point thread. Only difference is that we don't let the tool, the cutting motion of the tool is not relying on the surface footage of the part rotating. The surface footage required for cutting is created by the tool itself by spinning. That means that we can have the part rotate super slow, like 1 RPM, and still get a very nice thread. And the main reason I want to do this because I have to do small threads, small internal threads. They have often basically no lead out. And thread milling with very low speed, rotation and lengthwise, allows you to control the depth super precisely and super carefully. So let's try this out. Let's chuck up a thread mill. I have 2 different kinds here, and try this out. I have those 2 styles of thread mill here. This is a single point thread mill. It has only one 60-degree point and four cutting edges, which doesn't matter in this case. We have 1 row of teeth here, and this allows you. This has no built-in pitch, so you can use this for multiple thread pitches. This one goes for threads from M5 to M8. That's a function of the clearance of the cutting edges. If you try to cut too large of a pitch with this, you run out of clearance on the cutting edges. So this is basically good to a 1.25 millimeter pitch. The other one, this one has multiple rows of teeth, and this has the pitch built into it. It's M3, so it's 0.5 millimeter pitch. And the idea behind these is you go down to almost to full depth that you want to thread, and you feed out. You do one spiral, one rotational motion that has the pitch associated with it. So you go down, you take one rotation with the C motion following the pitch, in this case 0.5 millimeter. Then you retract to the center of the bore, you go out, and you have your thread cut in one go. That's basically the idea behind these. These are super fast. With this one, you have to spiral down the whole thread or spiral out. Most people prefer to go to the bottom of the bore, feed out, and then spiral out because of the chips packing up in the bottom of the thread. I use this style on the Datron at work. They work quite nice. So let's chuck this one up on the lathe and cut a little bit of a thread. Get the cutter chucked up in the router spindle here. We're going to run this at 15,000 RPM. First we will chamfer the end. So I will cut away from the chuck. That means I will have the lead screw in the normal feed direction, but have the spindle run in the reverse. The cutter here doesn't care about the direction of rotation, except for climb cutting or conventional cutting. With going reverse, we are conventional cutting, which is not ideal, but it is what it is. So we start by chamfering the end. Now we move in. Let's say we want to cut 10 millimeters of thread. We will cut a relief with this cutter. We will just plunge in straight without any lead screw motion. Okay, now we can feed in and engage the lead screw. And we just cut a beautiful 0.5 millimeter pitch thread instead of 1 millimeter pitch because I was too dumb to check the gearbox of the lathe. But let's finish this quickly. Due to the fact that I messed up the pitch, the feed pitch, we also cut thread way too deep because I went for a 5mm minor diameter, and that's about 0.5mm too small, and that had the cutter remove a lot of material. It was not necessary. So let's flip the part around and give it another shot. This is most likely not deep enough because those thread mills, those single point thread mills, don't have corner radius. The depth of cut is not what you expect them to be. There we go. A little bit too, yeah, it's okay. It's not terrible. Nothing to be ashamed of. But now I know that for an M6 thread with this cutter I have to go 1.5mm diameter reduction, because the crest of the thread is not rounded. So with that knowledge, we should be able to just drop down the cutter into the material, or 1.5mm diameter reduction, and cut the thread in 2 passes, one roughing, one finishing pass. Let's try it towards the chuck climb cutting situation. There we go. I forgot to chamfer the end, so let's do that. Oh, let's see. Should fit, hopefully. Otherwise I will edit it. Oh, there we go. Yeah, about the same fit as before. And you saw me, I turned the spindle off a tiny amount before I pulled the tool out, and I spun the chuck by hand until I hit my exact C location on the digital, and this allows for exceptionally precise length control on the thread. And no lead out, just retracted the tool. I'm very optimistic that this might help me in the future with some of the crazy parts that I do with an M2.5 thread with no lead out internally, of course. And the finish is also not, it's not excellent. The spindle motor, the router here, has its limitations rigidity wise, but it works. And also these super long shanked, this doesn't help either. I switched to the other style of thread mill, and the idea now is the lead screw is engaged. I set the lathe to 0.5mm pitch, and I turned the spindle a little bit counterclockwise to take out all the slack in the drivetrain of the lead screw. Backlash is just something you have to take into consideration with a manual lathe. And now we will just plunge in to full depth after we touched off on the OD, and then we will have the lathe go reverse and feed out. In theory, it would be enough to take one revolution, but I think it's better in this case to just have the thread mill come off the thread completely and act almost like a spring pass itself. And there we go, that's an M3 thread, a little bit on the tight side. The other thing you can do with these Threadmill, you can start here and just feed in like this. Does work the same, but then you don't take the advantage of the multitude of cutting edges here. So both things work. That's a multi-tooth cutter, but we can do more crazy things with with something that is a live tool on a manual lathe. Okay, and since I have the Decal S1 tool and cutter grinder now, I'm able to grind very fragile, very small, very precise tooling. So I tried to grind a 6mm OD thread mill, which kind of worked. Both are high-speed steel, and both are 4-fluted for cutting edges. And I also ground a tiny one with a 2mm OD on front here. Let's get this out of the way. And this one is also a 4-fluter. You can see the tiny relief flats on the back. This is hard to grind. I will not lie about it. This is tough to grind. You see, it's hard to see the grinding wheel. I'm using a tiny grinding wheel because I don't want to grind into my collet. The grinding wheel breaks down quite fast. You have to dress often. It just takes some practice. In carbide it might be easier using a diamond wheel, or in high-speed steel using a CBN wheel. I was using a tiny aluminum oxide wheel which broke down basically immediately. But still works. I can grind these now myself from scratch. That was a test cut with the larger 6mm thread mill that I ground, and it cuts actually beautiful. The thread is a little bit loose because I took the full depth in one cut and didn't do a test cut beforehand, but yeah, it works. Cuts nice and freely, so obviously the S1 grinder gives me the capability of grinding a functioning multi-flute thread mill. Let's try the small one to mill a 3mm thread. I fully expect this to break. Okay, let's see what we created here. Probably a mess. A little bit sloppy, but it threads in. It's sloppy because when I tried to touch off on the inside of the bore, I think I touched off a little bit over ambitious, and that way made it way oversized. Let's mill it open and have a look. I took it apart and milled it open to about half the thickness, and you can see the large M6 thread out here with 1mm pitch, with a nice fully formed V, which the correct thread profile would not have. The correct thread profile for a 6mm 1mm pitch thread would have quite a substantial radius here in front on the root of the thread. This is a full profile threading insert for 1mm pitch, and this has the correct radius here. Thread milling with those single point geometry does usually not create a 100% gauge fit thread. The thread gauge will fit, and the no-go gauge will also not fit if all the diameters are correct, but the thread profile is not dead on. So let's put on some more magnification and look a little bit closer. That's a lot of macro, but at least we see something. Let's take this apart. This is my toothpick. Here you can see the 1mm pitch thread profile, and in here that's the thread, the 0.5mm M3 thread, which is a little bit oversized. Let's find an M3 screw and place it in the thread. Here you can see that the pitch of the screw matches nicely with the pitch of the thread, which is a given because I set the lathe to 0.5mm pitch, but also the profile of the screw goes nicely into the profile of the milled thread, with a little bit of gap because, well, it's oversized. But I'm pretty pleased. I'm pretty pleased about the ability to thread mill and also grind my own thread milling cutters. Here's a close-up of the larger thread mill. This is the cutting surface, and here's the clearance angle to the back. 4 flutes, and I accidentally undercut the head of the milling portion here quite a bit. In an ideal case, this diameter here would go straight up to the cutting edges all the way. This fluting cut here, this is okay, this can go into the shank, but this neck here, this is not ideal. I have to find the right way to grind this without necking into there. That's the smaller thread mill. It's a 3mm shank. High-speed. Both of these cutters are ground from high-speed steel, and the necked down portion here is about I think it's 1mm, and this cutting portion in front here is 2mm. And as you can see, it all gets awfully. You can see all of this gets awfully small, and this is on the edge what I can grind on the S1 without any additional magnification. And even for this, a microscope on the grinder would be crazy useful. And I mean, a real microscope would be nice, not one of those video microscopes. I usually prefer an optical microscope, but I might try one of those video microscopes with the built-in displays just because they are cheap as dirt. But yeah, this is promising. There is another application that I want to use this for, and that's machining PVC. PVC is easy to machine. It's soft, but the problem is it's on a manual lathe. It's close to impossible to break the chip. Deburring is not an issue. You can run a feed and tool combination that will break the chip in Deburring super nice and super short, almost like brass. But in PVC, the feed has to be that high that it's not controllable by a human being anymore. On a CNC machine, you can run the feed high enough to break the chip, but not on a manual machine. If you want to hit any length tolerances or something like that. And I yeah, a lot of people recommend to use a dust extractor to just catch the long stringy chip off the lathe tool. That works, but then you have this 25.5 kilometer long chip whirling around in your shop vac and clogs things up, and that's not ideal too. So I considered if we can't break the chip by increasing the feed, why not just make an interrupted chip with a milling cutter? This uses to be a 6mm 4-fluid roughing end mill, and this works. Oh yeah, this is cool. I like this. I will use this for producing these parts. And this part was even only held in the 3-jaw chuck with the gripper jaws on very little amount of material, so the cutting forces cannot be very high. But the router motor bogged down. This is like 1,000 watts, 1 kilowatt. Intake power consumption of this router motor. Spindle power is significantly less because of losses, but still bogged down. So we're taking a substantial amount of material off in a reasonably short amount of time. We can also do weird things like orient the spindle 90 degrees to the spindle of the lathe and cut features like that. I have a 90-degree V-bit in here, and I set the lathe to a pitch of 2.5 millimeters. So let's see what we can do with this. And when we remove such large amount of material, the low spindle speed of the lathe is rather important. Think of having your power feed on the mill go too fast, and that's what would happen here too, especially on a single point cutter like this, on a D-bit. These are not especially known for a high material removal rate, but we can cut features this way too, and you could even do thread milling that way, but it's not ideal. I think you don't get the proper profile. I think you get some kind of weird recutting effect, but don't quote me on that. But you could, for example, cut oil grooves in a part, especially if you set the lathe for very high pitch rates. I think the MCO here tops out at 4 millimeter, but if you switch some gears around and some change gears, you can get it definitely to run higher pitches. You can cut oil grooves on the inside with a ball end mill, or a lollipop end mill that has a 240 degree engagement possibility. You can cut. You could even mill square threads on the outside of a part. Or using a T-slot. A T-slot cutter on the inside doesn't work because it has no clearance to the bottom. It would deform the profile heavily. So it has definitely its limitations. You would need the ability to tilt the spindle to do some things. Also for thread grinding on the lathe, you would have to tilt the spindle. But I'm not after that here on this machine. I need this really primarily for thread milling small diameter threads. This is just fooling around now, which is also fun and important to do sometimes, because you gain a little bit of confidence what's possible. So I hope you enjoyed. Thank you all for watching, and I'll be back.